Good evening, everyone, and welcome to session 36 of Essence Training Series. Today we have Dr. Ghosh going over the last lecture in Seismic, and he will be going over non-structural components and non-building structures. With this, I will transfer the mic to Dr. Ghosh.
Thank you, Bodhi, and good evening, everybody. As Bodhi mentioned, this is the last of our seismic offerings. We had 8 sessions planned. Today is the 8th, and I will talk about non-structural components and non-building structures. Non-structural components are treated in chapter 13 of AC 7 and the non-building structures in chapter 15. Before I get into today's topic, yesterday when I discussed building separation, I did mention that AC 705 did not have much of a provision that AC 7 did, and this is why I switched to AC 710 when it came to that discussion. At that time, I did not bring up BNBC 2020. I vaguely recalled that I had seen something there, so I looked it up after the seminar. And I think it will be not good to leave that out. So let me take you through what BNBC has to say about building separation, and then we will go on to today's topic. This should not take long. So this is BNBC section 2.5.14.3, separation between adjacent buildings. Exactly what we discussed yesterday. Buildings shall be protected from earthquake-induced pounding from adjacent structures or between structurally independent units of the same building, maintaining safe distance between such structures as follows. Maintaining safe distance. Okay, so as follows. Number 1 is for buildings or structurally independent units that do not belong to the same property. The distance from the property line to the potential points of impact shall not be less than the distance from the property line to the potential points of impact shall not be less than the computed maximum horizontal displacement of the building at the corresponding level. So I do not know how, let us read it. So for buildings or structurally independent units, so we are talking about more than one building, more than one structurally independent units, but they do not belong to the same property. The distance from the property line to the potential points of impact between the two buildings shall not be less than the computed maximum horizontal displacement of the building at the corresponding level. I think you understand the essentially they are saying that the setback distance, so there are two buildings in question. And if pounding happens, the shorter building will hit the taller building at the roof level of the shorter building. So the setback distance has to be the maximum horizontal displacement of the shorter building, and the setback distance for the taller building will be the maximum horizontal displacement at the level of the roof of the shorter building. Okay. Now, the concept of the maximum inelastic response displacement, as it was called in AC 710, where we specifically include torsional deformations, is not there in BNBC. The second item, for buildings or structurally independent units now belonging to the same property, if the distance between them is not less than the square root of the sum of the squares of the computed maximum horizontal displacements of the two buildings or units at the corresponding level. So this is exactly the same as AC 710. Separation distance is square root of the sum of the squares of the deflection at the roof level of the shorter building and the deflection at the corresponding level of the taller building. Okay. Now, this square root of the sum of the squares concept is in BNBC ahead of AC 710. I wanted you to see that. And once again, we are not talking about delta sub M1 of AC 7, including torsion. This is the horizontal displacement. Okay. It may not include torsion. Then that is what I found the most interesting, and the reason that I thought that I had to show all of this to you is item number 3. If the floor elevations of the building or independent unit under design are the same as those of the adjacent building or unit. Okay, please let me read that again. So if the floor elevations of the building or independent unit under design are the same as those of the adjacent building or unit, the above referred minimum distance may be reduced by a factor of 0.7. Remember, I told you yesterday the main thing is the alignment of the floors. If floor hits against floor, not much damage typically happens. The problem is when floor hits against the column. So here, BNBC is saying if the floors are aligned, then you can reduce the gap 30%, which makes a lot of sense to me. I have never seen that in any code. I told you yesterday that this kind of thing is very difficult to codify. So I think this is very interesting, and you should take note that it is in BNBC. Okay, moving on to today's topics. What we will discuss are AC7 BNBC requirements for non-structural components. Those are covered in BNBC 2020. Then ASCE requirements for non-building structures. Those are not covered in BNBC. BNBC simply references ASCE 7. And non-structural component versus non-building structure. This is a discussion of a question that comes up all the time. You have to design a tank that is, let us say, mounted on top of a building. Is the tank a non-structural component or a non-building structure? Many times it is a question without an easy answer. So that topic I want to spend a little bit of time on. Okay. So the documents in the background of our discussion are BNBC 2020, the seismic provisions of which are based on those of AC 705. You have heard this many times. Those are still in the background. Today, I do not know that I will need to go too many times to AC 710. So, but let's see. Okay. As I mentioned already, the non-structural components are in chapter 13. and non-building structures are addressed in Chapter 15 of ASCE 7. The non-structural components can be architectural components, mechanical or electrical. The architectural components are treated in Section 13.5. The mechanical and electrical components are treated in 13.6. Now, these things, the non-structural components, could be a parapet, which would be an architectural component, or an or an elevator, which will be a mechanical component, or cables, electrical cables, which would be electrical component. All of these things in the days of the Uniform Building Code used to be called parts and portions. So everything to do with those has a subscript P in BNBC for parts and portions. So we talk about I sub P for importance factor of parts and portions, or R sub P for response modification factor for parts and portions. In BNBC, the subscript is C for component. It's not P. Now, whether it was necessary to change that, I do not know what has been gained by that kind of a change. But this is something you need to catch on to if you're going to correlate the two documents. Okay. So non-structural components are architectural, mechanical, electrical, and a building typically has a lot of them. An office building, you have false ceilings, the lighting fixtures, the telephone cables. I mean, the you know, the structure of a building accounts for 25% of the cost of the building. Everything else is in the broad category of non-structural components, and those account for up to 75% of the cost of a building. So the when there is damage to these in an earthquake, it is definitely a lot of money that we are looking at. But more importantly, the function of the building is disrupted. It is very difficult to work in a building where there are no lights on, there is no air conditioning, and that sort of thing. So the non-structural components, their importance absolutely cannot be minimized. Okay, the architectural components that are listed in table 13.5-1 of ASCE 7. They are listed because in their design, we need factors that are given in those tables. So these are the ones that are listed, and that will give you a good idea of what we're talking about. So non-structural walls and partitions, okay, you are all familiar with them. Parapets and chimneys, these are roof-mounted chimneys. Exterior non-structural wall elements and connections, veneer, penthouses, ceilings, cabinets, if the cabinets are attached to the structure. Otherwise, it will be treated as furniture, and furnitures are typically not considered non-structural components. It is when they are attached to the structure or braced against the structure, then we do consider them. Access floors, signs, billboards, appendages of various kinds, and glazing or glass, very important architectural components. Mechanical components, these are listed in table 13.6-1, very important table. Boilers and furnaces, HVAC, this is heating, ventilating, air conditioning, could be ducts, could be equipment, piping systems, engines, turbines, fans, furnaces, chillers, elevators, escalators, all of that, mechanical components, electrical conduits, bus ducts, cable trays, lighting, the lighting fixtures. Okay, for the purposes of this chapter, chapter 13 of AC 7, non-structural components shall be assigned to the same seismic design category at the structure that they occupy or to which they are attached. Okay, so very simple. The seismic design category of the non-structural components are the same as those of the structure. Now, at the beginning of chapter 13, and the same is true in BNBC. In BNBC, it is 2.5.15, as you see. There are a number of exemptions. That's pretty much where the chapter starts, where the requirements do not apply. And that is a very important list because it is only the other non-structural components that you need to design using chapter 13. So there is to start with a list of non-structural components that need not be designed using chapter 13 of AC 7 or 2.5.15 of BNBC 2020. Okay, so this section establishes minimum design criteria for non-structural components that are permanently attached to structures and for their supports and attachments. So this is non-structural components permanently attached to the structures. This is not furniture, as I said. And for the supports and attachments of those non-structural components. Okay, if they're attached to the structure, the attachment has to be designed. The following components are exempt from the requirements of this section. Okay, so the following are exempt: architectural components, seismic design category B. Okay, that's obviously a big exemption. Architectural components in design category B, other than, so not exempt, are parapets supported by bearing walls or shear walls, where the component importance factor is equal to 1. So architectural components in design category B, where the component importance factor is equal to 1. But the parapet supported by bearing walls and shear walls is not exempt. Okay, so architectural components, design category B, I sub P of 1. Then mechanical and electrical components, design category B, irrespective of I sub P. Okay, all of them. Then mechanical and electrical components, design category C, where I sub P is 1. They're all exempt. Continuing, mechanical and electrical components, design category D, where the I sub P is equal to 1 and either flexible connections between the components and associated ductwork, piping, and conduit are provided. So connections between the component and pipes and things that are feeding into the component are flexible connections. Or not and. This is or. Components are mounted at 4 feet or less above the floor level and weigh 400 pounds or less. Okay, so this is equipment close to the floor, not very high up, not too heavy, 400 pounds or less, flexible connections with piping and so forth. If all of that is true, then even in design category D, you can exempt them provided I is equal to 1. And we will take a look at where I sub P comes from. Okay, what I sub P of 1 actually means. Final one, mechanical and electrical components, design category C or D, where I sub P is 1, and flexible connections between the components and associated ductwork, piping, and conduit are provided. In this case, it is and, not or. And the components weigh 20 pounds or less, or for distribution systems, they weigh 5 pounds per linear foot or less. So anyway, you have to read them closely. I think they're totally understandable upon reading. But the main thing is that there is a significant list of exemptions to start with. Now, there is a provision in BNBC which I first of all don't fully understand. Secondly, I do not know what you do with something like this. Let's take a look. So where the individual weight of supported components and non-building structures. So it says individual weight. And that kind of throws me. Where the individual weight of supported components and non-building structures with periods greater than 0.6 second, that is typically indicative of a period is 0.6 second up to 0.6 second, which is very, very short. It is considered to be rigid. And after that, it is not rigid anymore. So where the individual weight of supported components and non-building structures with periods greater than 0.6 second exceeds 25% of the total seismic weight W. The individual weight is what I don't understand. They're not talking about combined weight. Individual weight of supported components. The structure shall be designed considering interaction effects between the structure and the supported components. Well, I think your interpretation would be as good as mine. I'm not quite sure exactly what we are being told. Testing shall be permitted to be used in lieu of analysis methods outlined in this chapter to determine the seismic capacity of components and their supports and attachments. Okay, that take that for what it is. Now in AC 7, there are more understandable and more specific requirements that are kind of important. I will spend a little time on this stuff because this tends to be extremely important, and it goes into the territory of what is a non-building structure, what is a non-structural component. Do you design something by chapter 13? Do you design it by chapter 15? So let us take a look at, what I tried to convey to you is that BNBC kind of talks about it, but what it says is vague at best. At least I don't understand it. Let us look at ACE requirements, where the weight of a non-structural component, okay, pretty clear cut, weight of a non-structural component is greater than or equal to 25% of the effective seismic weight, W, which is defined, includes the weight of the non-structural component. Okay. The component shall be classified as a non-building structure and shall be designed in accordance with 15.3.2. So this couldn't be any more clear cut. If a non-structural component is heavy, weighs more than 25% of the total weight of the structure and the component, then you shall design this non-structural component as a non-building structure. Okay. Non-building structures, including storage racks and tanks. We are now talking about non-building structures, not non-structural components. Okay. So non-building structures, including storage racks and tanks that are supported by other structures, shall be designed in accordance with Chapter 15. We kind of know that. Where Section 15.3 requires that seismic forces be determined in accordance with Chapter 13. I will take you there. Please note, this is important stuff because I have had dealings with this stuff where I have dealt with situations where this turns out to be very important. Yeah. So non-building structure shall be designed by Chapter 15. That's fine. But then Chapter 15 may direct you to Chapter 13 for the design of certain non-structural components. That's what we are talking about in the second sentence, where Section 15.3 requires that seismic forces be determined in accordance with Chapter 13 and values of R sub P are not provided. If you want to design by Chapter 13, you will need the component response modification factor R sub P. So when Chapter 15 directs you to Chapter 13 and R sub P is not provided, R sub P shall be taken as equal to the value of R listed in Chapter 15. So you would take the R value from Chapter 15. The value of A sub P, this is dynamic amplification factor, shall be determined in accordance with footnote A to tables 13.5.1, 13.6.1. Anyway, details aside, what I'm trying to indicate to you is that non-building structures that are supported by other structures shall be designed by Chapter 15. But there are times when Chapter 15 will tell you that certain non-building structures shall be designed by Chapter 13. And then you will need R sub P, A sub P, and where you get it is indicated here. Okay, next is where non-building structures identified in table 15.4-2. I think I said yesterday or on prior occasions, yesterday definitely, that every non-building structure is put into one of two categories by Chapter 15. Non-building structures similar to buildings and non-building structures not similar to buildings. The classification does not quite depend on what the non-building structure looks like. It depends on the seismic force resisting system that is used in the structure. If a non-building structure uses a seismic force resisting system that is listed in table 12.2-1, which is the seismic force resisting system for a building, then it is a non-building structure similar to buildings. If that is not the case, if the seismic force resisting system is not one that is listed in that table, then you have a non-building structure not similar to buildings. Okay. The non-building structures similar to buildings are in table 15.4-1, and the non-building structures not similar to buildings are in table 15.4-2. So where non-building structures are identified as not similar to buildings, a non-building structure that is not similar to building, when it is supported by other structures, and the non-building structures are not part of the primary seismic force resisting system, one of the following methods shall be used. Let's read this you need to understand. So where non-building structures that are not similar to buildings are supported by other structures, okay, could be a chimney, and the non-building structures are not part of the primary seismic force resisting system, then one of the following methods shall be used. I'll take you only through the first part. The second part is a little too complicated, and I'll leave it to you to read if you're interested. For the condition where the weight of the non-building structure, so we are talking about a non-building structure supported on another structure. For the condition where the weight of the non-building structure is less than 25% of the combined weight of the non-building structure and supporting structure. Okay, this is the important part. Where the weight of the non-building structure is less than 25% of the combined weight of the non-building structure and supporting structure, the design seismic forces of the non-building structure shall be determined in accordance with chapter 13. See, this is where it sends you. Chapter 15 sends you to chapter 13, where the non-building structure has a weight that is less than 25% of the combined weight of the, okay. So shall be determined in accordance with chapter 13, where the values of R sub P and A sub P shall be determined in accordance with section 13.1.5, which we looked at. Okay. Anyway, the rest of it may or may not be all that terribly important, and I will not take you through the case where the non-building structure weighs more than 25% of the combined weight. Sorry about that. I forgot to put it on silencer today. Okay. So where the non-building structure weighs more than 25% of the combined weight, I will not take you through that, but there is provision for that. So I wanted you to see that instead of this vague provision in BNBC 2020, AC7 has very clear, distinct provisions for both non-structural components and non-building structures. And these are kind of interrelated. Okay. And I think that's probably enough on this topic. But this is the exemptions are very important, and what I just took you through is also very important. It is. I mean, you cannot start doing things. You cannot start designing a non-structural component without figuring out if it is exempt, because then you'll be wasting time. And also you cannot start running numbers until you have figured out some of the things that we discussed. Is the non-structural component too heavy? In which case we may have to go to chapter 15 for our design, not chapter 13. Okay. So With those things settled, so let us get into chapter 13, the non-structural component design chapter. So if you consider the exemptions, then what that leaves for us to design are parapets in design category B, all parapets, and architectural components in design category B when I sub P is larger than 1. Okay, so in seismic design category B, the only architectural components that we need to design by chapter 13 are parapets and architectural components with I sub P larger than 1. If the design category is C, all architectural components must be designed by chapter 13. Electrical and mechanical components must be designed, but only if I sub P is larger than 1. Design categories D, E, and F. Architectural, mechanical, electrical, all non-structural components. Basically, always shall be designed by chapter 13. We say basically always because there were those exemptions 4 and 5, remember? These exemptions are there for the high seismic design categories. But other than, and those are not broad exceptions, those are kind of narrow. So this is why we are saying basically always. So design category B, parapets have to be designed using chapter 13. Other architectural components provided I sub P is larger than 1. Design category C, all architectural components, electrical, mechanical only when I sub P is larger than 1. Design categories D, E, and F, basically all architectural, mechanical, electrical components. Now the I sub P that keeps on coming up. Okay, I sub P, as you have seen, is very important. It dictates many times whether we have to design a component by chapter 13 or we can forget about design. Okay, so I sub P is component importance factor. It is given in section 13.1.3 of AC7. I have given you the corresponding BNBC section number. I sub P is either 1 or 1.5. Okay. I for the structure can have 3 values, 1, 1.25, or 1.5. I sub P for parts and portions has only 2 admissible values, 1 or 1.5. This is the section where you determine I sub P, component importance factor. The factor shall be taken as 1.5 if any of the following conditions apply. You shall take the I sub P equal to 1.5 if any of the following conditions apply. The component is required to function for fire safety purposes after an earthquake, including fire protection sprinkler systems. Okay, pretty clear cut. 2, the component contains hazardous materials, which when released can do harm to the public. And 3, the component is in or attached to an occupancy category 4 structure. Those are essential facilities and hazardous facilities. and is needed for continued operation of the facility, or its failure could impair the continued operation of the facility. Okay, so 1, 2, 3. Those I sub p shall be taken as 1.5 if any of the following conditions apply. And then I should have had a break here. All other components shall be assigned an I sub p of 1. Okay, so I sub p is 1.5 when those conditions are met. It's kind of, it's not exactly essential facility, but the component is needed for continued functioning of a facility. The language is clear. Otherwise, I sub p is equal to 1. Okay. Uh, what force do you need to design a component for? The component design force is F sub P. Okay. That notation is common between AC7 and BNBC, F sub P. Maybe it is F sub C. Yeah, F sub C in BNBC. Okay. So the component design force is 40% of S sub ds. S sub ds, remember, is short period design spectral acceleration. If we divide that by 2.5 or multiply it by 0.4, we get design level peak ground acceleration. Okay, this we have discussed many times before. So we are talking about the peak ground acceleration multiplied by a dynamic amplification factor, A sub P, times the weight of the component, W sub P, divided by R sub P, component response modification factor, and then I sub P is the importance factor we have been talking about. Okay, so it's basically 0.4 S sub ds times W sub P. The peak ground acceleration multiplied by the weight of the equipment. Okay. Then we multiply by a dynamic amplification factor A sub P and an importance factor I sub P. I sub P you have seen already. A sub P we will talk about. And we divide the whole thing by a component response modification factor. This is the same concept as R factor for the whole structure. This is for the component, okay? In recognition of inelastic response in the design earthquake. Now, all of that together will give you the design force on a component that is, let us say, mounted on the ground. We are taking the peak ground acceleration. If the component is on an upper level of a structure, then this part comes into the picture. Okay. Z is any height above ground level. So if you have mounted your equipment 20 feet above ground level, and H is the roof height, if your building is 40 feet tall, then 20 by 40 will be 1/2 times 2 will be 1 plus 1 will be 2. So your component design force will be twice that for a component mounted on the ground. I hope everybody with me. Z is any height above ground level, and that's where the component is mounted on the structure, attached to the structure. H is the roof height. So the component design force increases from this value to 3 times this value for a roof mounted structure. If a component is mounted on the roof, then Z will be equal to H. So that will be 1, and then 1 plus 2 will give us 3. So a roof mounted component will be designed for 3 times the force of a component mounted on the ground. Okay. In BNBC, this is your equation. F sub P is F sub C. This part is exactly the same. I sub C is I sub P, R sub C is R sub P, W sub C is W sub P. Anyway, so alpha sub C and A sub H. Alpha sub C is the same as A sub P, the dynamic amplification factor. So A sub H takes the place of 0.4 S sub ds. Okay, that's what it boils down to. If you compare the two equations, alpha sub C is A sub P, W sub C is W sub P, I sub C is I sub P, R sub C is R sub P. And then 1 plus 2 Z over H is the same as in the AC7 formula. So this A sub H takes the place of 0.4 S sub ds. And here I'm showing you that that is the case. A sub H, in fact, is equal to 40% of S sub ds. A sub H in BNBC is given by this expression, 2/3 Z times the soil factor S. The soil factor S of BNBC is F sub A of AC7, and the Z is 40% of S sub S. Z is MCE level acceleration. This is why it is 40% of S sub S, not S sub ds. So 2/3 of Z, which is 40% of S sub S, times the soil factor S, which is the short period site coefficient F sub A, and all of that, 2/3 of S sub S, F sub A is S sub ds. So A sub H is actually equal to 40% of S sub ds. So there is absolutely no difference between the BNBC formula and the AC7 formula. If you remember that alpha sub C is A sub P, and in all other cases, the subscript C is subscript P of AC7. Okay. So what is A sub P? That's the dynamic amplification factor. It is given in table 13.5-1 for architectural components and table 13.6-1 for mechanical and electrical components. Okay. R sub P is given in those tables. A sub P is also given in those tables. 13.5-1 for architectural, 13.6-1 for mechanical and electrical. A sub P is either 1 or 2.5 with just one exception, just so that you know. There is either no dynamic amplification or there is significant dynamic amplification, 1 or 2.5, with one exception. I did not reproduce table 13.5-1. It is easy enough for you to look up. I think I gave you the corresponding BNBC table number. Anyway, that's where it comes from, and it is 1 or 2.5. That's obviously important. Okay, now we will discuss the variation along height that we, in a way, already discussed. So at the base of the structure, the peak acceleration is 40% of S sub ds. I said base of the structure, technically 40% of S sub ds is at the ground level. Okay? And base is a defined term in ASCE 7. This is where seismic forces are imparted to the structure. Seismic ground motion is imparted to the structure. This is how it is defined. It is up to the engineer to decide what the base of his structure is. Now, if it is a structure on a level, on level ground, the ground level is typically chosen as the base. But 40% of S sub ds is peak ground acceleration, and that would typically be the acceleration at the base. At the roof level, we are considering 3 times as much acceleration, and in between it is a linear variation, and that is what is expressed by this expression. Okay, so for equipment, piece of equipment A, which is mounted at a height of Z sub A above the ground level, the component design force is equal to that, ZA over H. And for equipment B, which is mounted at Z sub B above ground level, this is the component design force, 1 plus 2 Z sub B by H. It's linear variation in between the base and the roof. Okay, so we discussed I sub P, the variation A sub P, and now the R sub P. That is about the only item in that equation that we have not discussed. It is component response modification factor, as I have been calling it. This is also given in the same tables, 13.5-1 for architectural components, 13.6-1 for mechanical and electrical components. The corresponding BNBC table numbers are given. R sub P ranges between 1 and 12. Now 12, I think there is only one case that is kind of an outlier, but it is a pretty big range. It is not like A sub P, 1 or 2.5. Okay, so in those tables, the architectural, mechanical, electrical components that I showed you earlier in the 3 earlier slides are listed, and their A sub P and R sub P values are given. Now ASC tells you a couple of things that you need to understand and keep in mind, and same language or very similar language is also in BNBC. The force F sub P shall be applied independently in at least 2 orthogonal horizontal directions in combination with service loads associated with the component as appropriate. Okay. So at least 2 orthogonal horizontal directions. That what do I want to say? Yeah, that's what should be done. But when you are designing a parapet, it is the out of plane direction that counts. In plane, this f sub p will not do anything. Will It will basically have no consequence. It's a it's a long thing. Anyhow, I want to say that in principle, yes. In reality, it may, depending upon what you are doing, it may not be necessary to apply the force, as it says, in at least two orthogonal horizontal directions. For vertically cantilevered systems, the force F sub p shall be assumed to act in any horizontal direction. In addition, the component shall be designed for a concurrent vertical force of plus or minus 0.2 S sub ds times the weight of the component. Okay, this can be plus or minus. This is on top of the lateral force, the F sub p. This is an axial force, a vertical. That cannot. I mean, I probably shouldn't say axial. It's a vertical force. The redundancy factor rho is permitted to be taken equal to 1, and the overstrength factor omega sub 0 does not apply. Okay. So read this and keep this in mind. The what you are designing will dictate exactly how you implement that requirement. Where non-seismic loads on non-structural components exceed F sub p, such loads shall govern the strength design. So let's say on a parapet you have out of plane wind, you have the F sub p acting out of plane. The wind may very well govern in high wind areas, and you will design for strength required for the wind, no question about it. Okay, so where non-seismic loads on non-structural components exceed F sub p, such loads shall govern the strength design, but the detailing requirements and limitations prescribed in this chapter shall apply. And this is like structure. Okay, the strength will have to be whatever requires the strength, but if your seismic design category is high, it will do the required detailing. Okay, so component design force. I hope that the requirements are clear. It's actually conceptually without any complication, as far as I'm concerned. Okay, 40% of S sub ds is the peak ground acceleration, design level peak ground acceleration. We multiply that by the weight of the component. So mass times acceleration is a force. So that's what we get. We have our component design force. That's the basic part. 40% S sub ds W sub P. Now there is a possible dynamic amplification depending upon what we are designing. Dynamic amplification would be like higher mode effects. And there is the possibility of a response modification factor if the response is going to be inelastic. That's where A sub P and R sub P come from. I sub P makes sure that we design important components for higher force. It's that simple. If a component is going to be needed for fire recovery after an earthquake, we better design it for 1.5 times the force that we would use in the design of ordinary components. And then all of that gives us the connection force for a piece of equipment mounted on ground. If it is a roof mounted equipment, we would multiply that force by a factor of 3. And we interpolate linearly between 1 at the ground level and 3 at the roof level. So something mounted at mid height of the structure shall be designed for twice the component mounted at the ground level. Okay, so the equation makes basic sense. The A sub P and R sub P are given in tables, making it easy. And I sub P determination we have talked about. So there is not much else that is in AC7 or BNBC. Now that is the force. There are some things like piping and so forth where the component design force is not important. What is important is seismic relative displacement that has to be accommodated by the piping or whatever we are designing. The effects of seismic relative displacements are required to be considered. That's what section 13.3.2 of AC7 says, and the corresponding section number in BNBC is that. So this is that section 13.3.2. The effects of seismic relative displacements shall be considered in combination with displacements caused by other loads as appropriate. So it's not only seismic that may cause displacements, other loads may also, anyway, so in combination with displacements caused by other loads. Seismic relative displacements, the notation is capital D sub P, shall be determined in accordance with equations set forth. Okay, so equations are given for D sub P. This is very likely D sub C in BNBC. Okay, so please follow this. So for 2 connection points on the same structure A, okay, so piping, whatever we are designing, is attached to the same structure at 2 connection points. For 2 connection points on the same structure A or the same structural system, 2 connection points, one at a height h sub x and the other at a height h sub y. This one, there should be a subscript. D sub P shall be determined as just delta sub xa minus delta sub y A. A is for the structure. So it is D sub P is delta sub x minus delta sub y, as simple as that. For 2 connection points on the same structure, one at a height h sub x, the other at a height h sub y, D sub P shall be determined as delta sub x minus delta sub y. Okay. Alternatively, to what we just said, D sub P is permitted to be determined using modal procedures described in 12.9. I took you through. It was one full day on modal analysis, remember. Alternatively, D sub P is permitted to be determined using modal procedures described in 12.9, using the difference in story deflections calculated for each mode, and then combined using appropriate modal combination procedures. D sub P is not required to be taken as greater than, okay? So D sub P you calculate. D sub P is not required to be greater than, not required to be taken any greater than, or simpler language would be D sub P need not be any larger than, okay? Let's see what this is. So H sub X is the height to the first attachment point, H sub Y is the height to the second attachment point. So H sub X minus H sub Y is the vertical distance between the 2 points, okay? We divide that by the story height, H sub Sx, and multiply by the allowable drift of structure A. So the actual relative displacement D sub P need not be taken any greater than delta allowable deflection, let's say point, let us say 2% of story height, okay? So delta sub A would be 2% of story height. We divide that by the story height, that gives us 2%. So D sub P need not be taken any larger than 2% of the vertical distance between the points where the piping is attached to the structure. Okay, so D sub P you will calculate as here, or you will calculate by modal analysis procedure, but it need not be taken any larger than the right hand side. So that is attachment to the same structure. For two connection points on separate structures A and B, one at a height H sub X and the other at a height H sub Y, D sub P shall be determined as absolute value of delta sub X, which is on structure A, and delta sub Y, which is on structure B. Okay, so we have the attachment point at H sub X moves. The attachment point at H sub Y also moves. We will take the horizontal movements and sum them up. Okay, absolute values, because the movement is in both directions. We will take the absolute values of the two and add them together. This D sub P need not be any larger than, same thing, we take the deflection limit, how much we'll allow, the allowable interstory drift, we divide that by the story height, multiply by H sub X. H sub X is the height to where the first attachment is. And similarly, we take delta sub A, the allowable story drift of structure B, divided by the story height, multiplied by height to the point where the second attachment point is. So I think if you read this, it will be clearer than I probably was able to make it. I think everything makes sense when you read. So then, so a component has to be designed for the force that we looked at. Depending upon the component, more critical combination consideration may be that you will have to accommodate the relative displacement D sub P that we looked at when you design glazing or glass. it is the relative displacement that becomes important. That has to be kept within tolerable limits that are given in AC7. Okay, so whether the force or the displacement is more important depends on what it is that you are designing. And then the attachment of the non-structural component to the structure, that obviously is important. You have to design that attachment as well. So the section is 13.4 in AC7, 2.5.15.2 in BNBC. I took the first two lines from BNBC because it's simpler, and then AC7 language, which is very, very similar to what you have in BNBC. Components shall be attached such that the component forces are transferred to the structure. Very simple, conceptually and practically, that's what we have to do. Component attachments shall be bolted, welded, or otherwise positively fastened, okay, positively fastened without consideration of frictional resistance produced by the effects of gravity. Friction due to gravity is not something we count on in seismic design. There are these days one exception. I would not go there, but from the beginning of seismic design, we have not relied on friction caused by gravity for seismic resistance. And we are saying the same thing. Component attachment shall be bolted, welded, or otherwise positively fastened without consideration of frictional resistance produced by the effects of gravity. A continuous load path of sufficient strength and stiffness between the component and the supporting structure shall be provided. The section goes on, and this part may be a little less simple to quickly follow. So local elements of the structure on which the component is attached. Local elements of the structure. It could be anything, but it is not the main columns, beams, shear walls. Local elements of the structure, including connections, shall be designed and constructed for the component forces where they control the design of the elements or their connections. Okay, it's not always that the force is controlled. It could be deformations, but anyway, the component forces shall be those determined in section such and such. We looked at that, except that modifications to F sub P and R sub P due to anchorage conditions need not be considered. So you take the component forces calculated from the formula that I showed you. Modifications to F sub P and R sub P due to anchorage conditions need not be considered. The design document shall include sufficient information relating to the attachments to verify compliance with the requirements of this section. Anyway, this may require more than one reading, but there is nothing that I think is confusing. Okay, the section 13.4 continuing, this is a subsection on design forces. The force in the attachment, we are talking about attachment in 13.4. Okay, attachment design. Remember, the attachment will transfer the force from the component to the structure. That's where we are. The force in the attachment shall be determined based on the prescribed forces and displacement for the component determined. So the component design force or the component design displacements will tell us what the attachment design force is. AC 710. So this language is in AC 710 as well. AC 710 has added except that R sub P shall not be taken as larger than 6. Okay. So the force in the attachment shall be determined based on the prescribed forces and displacements for the component determined from earlier provisions, except that R sub P shall not be taken as larger than 6. The next subsection, very important under attachments, is anchors in concrete or masonry. Okay. Masonry I have not reproduced, but the subsection on anchors in concrete, AC 705 has 4-5 provisions. If you read them, you are liable to be confused. And then in AC 710, we switch to this requirement. Anchors in concrete shall be designed in accordance with Appendix D of ACI 318, the anchorage appendix. Okay. Anchoring to concrete is the title of Appendix D. So, and that takes care of everything that AC 705 was telling us to do. So this is a very, very important requirement when you attach a non-structural component to a structure. The anchors shall be designed using ACI 318, Appendix D, and that will give you ductile anchor failure. ACI insists on the steel failing rather than concrete in anchor design, and the steel failure has to be ductile failure. Okay, there are a couple of alternatives to that, but anyway, so that kind of a failure mode is very, very important. So this to me is an extremely important requirement, that the anchors must be designed by ACI 318. Okay. Now, beyond anchor design forces, anchors in concrete or masonry, there are other provisions that you need to look at in AC 7. Installation conditions, multiple attachments, power actuated fasteners, and even friction clips. And there is good commentary on friction clips with a picture. Okay, good AC 7 commentary. So as far as anchorage of non-structural components, there is quite a bit said in AC 705. In ACE 7, a big item is special certification. I didn't quite find it in BNBC. That doesn't mean it is not there. I may not have found it. Special certification is required for many equipment. And anyway, let's look at this. Hospital equipment, a hospital will not buy equipment that does not have special certification on it. It's as simple as that. So this is a very important requirement of AC 7 that is adopted by the IBC and practiced across the United States. So where in the code do you find special certification requirements? AC 705, it is section 13.2.2. This is in the IBC as well. I went back to 2009 IBC because that's more like BNBC 2020. And the section where you find special certification is 1708.4. Chapter 17 is on inspection and testing. Okay. What does certification applies to? For what do you have to have special certification? Design category C through F, mechanical and electrical equipment with I sub P larger than 1. This is very, very important stuff. Okay. Design category C through F, mechanical and electrical equipment, all mechanical electrical equipment that has I sub P larger than 1. Also, design category C through F components with hazardous contents that have I sub P larger than 1. Okay. Now, if you read ASC 7, instead of straight out saying equipment with I sub P larger than 1, it talks about the designated seismic system. Designated seismic system consists of electrical mechanical equipment with I sub P larger than 1. The definition is in section 11.2. Anyway, so what it boils down to is what we said here. What do you need special certification for? Design categories C through F, mechanical and electrical equipment with I sub P larger than 1. Design categories C through F components with hazardous contents I sub P larger than 1. Okay. So what is required special certification? What basically is this special certification? For mechanical and electrical equipment, show that equipment remains operable following design earthquake, and this showing has to be by shake-table testing in accordance with such and such, experience data in accordance with 1326, or analysis. So the basis can be shake-table testing, experience data that would be acceptable to the building official, or analysis. Analysis choice is kind of restricted. You cannot always use it. But anyway, the purpose of the shake-table testing and so forth is to show that the equipment remains operable following design earthquake. Okay, and the special certificate will state exactly that. For components with hazardous contents, show that containment is maintained. The material will remain contained following design earthquake. And you shall also show this by shake-table testing or experience data or analysis. On top of everything we discussed, IBC has special inspection requirements for some of this stuff. For storage racks and access floors, periodic special inspection is required. Periodic means from time to time as opposed to continuous. For architectural components, also periodic special inspection. And mechanical and electrical components, periodic special inspection. I have given you IBC section numbers. Those are 2009 IBC section numbers. So you can see what the requirements are. So it is a pretty comprehensive package. Beyond the general requirements, the design force, the relative displacement, the tables giving us A sub P, R sub P, there are specific requirements for many non-structural components in chapter 13 of ASC 7. And those things for which we have specific provisions are exterior walls and connections, glass, suspended ceilings, access floors, partitions. Those are all architectural components. Mechanical electrical components for which we have specific provisions printed in AC 705 are utility and service lines, HVAC ductwork, piping systems, boilers and pressure vessels, elevators and escalators. Okay. So that brings us to a point that is, I think, very logical for our break. So we will come back at 9:35 precisely and go into the non-building structures. Okay.
Dr. Ghosh?
Yeah,
So I think you will finish quite early today because there's not much left after this,
I
right?
don't know. We'll see.
Okay.
Could happen. It should be good.
Yeah, then I was thinking that I will leave the question and answers for you then today.
Oh, whatever you like. Yeah, I
Yeah,
don't know. How many slides left?
let me check. There are not many slides left after this.
Yeah, anyway, if it is early, that would be good.
Yeah, I think 29, 30 slides.
Yeah. It probably won't be that early, but probably a little early.
Yeah.
Yeah.
Okay.
Yeah.
Okay.
Okay, it's time. So let's start. Non-building structures, you see the variety that is all around us. Uh, Hard and fast definition of non-building structure is really not available. We kind of know that these are not buildings, and uh, to try to go beyond that is not easy or simple. So let us not try. But these are all non-building structures. Everything in the picture. It can be just a tank, one individual tank. It could be a transmission tower like that, or it could be an entire facility, an entire refinery. Okay, a refinery would have multiple non-building structures in it. Anyhow, uh, BNBC simply does not cover the non-building structures, important as they are. This is what is in BNBC 2020. The section number is 2.5.18. Calculation of seismic design forces on non-building structures such as chimney, self-supported overhead water/fluid tank, silo, truss tower, storage tank, cooling tower, monument, and other structures not covered in section 2.5 shall be in accordance with chapter 15 seismic design requirements for non-building structures, minimum design loads for buildings and other structures. So AC 705 chapter 15 is where you are being asked to go to, okay, complying with the requirements of section 2.5 of this code. So when it comes to design, so there is no difference between section 2.5 and AC 7 anyway. So in other words, BNBC directs you to chapter 15 of ASC 7. ASC 705 scope section, and I didn't put the section number here for some reason. I meant to. It's 11.1.1 if I recall correctly. The scope of the seismic provisions. So the section spells out the scope of the seismic provisions of ASC 7, but then there are exceptions, things that are not covered by ASC 7. Exception 4 includes the items that I have listed: vehicular bridges, electrical transmission towers, hydraulic structures, buried utility lines, nuclear reactors. Those are all non-building structures, but they are not covered by ASC 705. The electrical transmission tower is kind of illogical for ASC 7 not to cover, but that is because of political reasons. The powerful interests didn't want ASC 7 to cover them. Be that as it may, ASC 7 tells you in black and white that those particular non-building structures definitely includes all bridges, are not covered by ASC 705. Okay, as I said, non-building structures are put into one of two categories: non-building structures similar to buildings, or non-building structures not similar to buildings. The non-building structures similar to buildings utilize seismic force resisting systems that are listed in table 12.2-1. A very common example are the pipe racks that you find in all kinds of plants. The racks are quite often made of concrete. In this case, it is precast. They don't have to be precast. The important thing is these are frames, the same frames that are listed in AC7 table 12.2-1. If your seismic design category is D, these frames will have to be special moment frames. Okay, none of that goes away. So that the fact that the seismic force resisting system is moment frames makes this non-building structure similar to buildings. The many water tanks or liquid retaining tanks that are all around us, we we typically, well, definitely from the outside, we wouldn't know what the seismic force resisting system is. And seismic forces may very well be resisted by systems that are not listed in table 12.2-1. So these are non-building structures not similar to buildings. Basically, non-building structures similar to buildings are treated like buildings for most practical purposes. We design them as we would design a building with some modifications, additions that we will talk about that are made in chapter 15. Non-building structures not similar to buildings, we have specific provisions for many of them in chapter 15. And something like liquid retaining tanks, the provisions have now, from the beginning in the uh, I'm thinking of, it's difficult to pinpoint when the beginning was, but let us say uh, the Uniform Building Code of the 80s had very little to nothing on non-structural components, non-building structures. So these are relatively recent. I would say started in the 90s, but then have really mushroomed. And the tank provisions of chapter 15 of ASC 7 occupy several pages, and those are sophisticated like you wouldn't believe. Okay, so anyway, if you have a non-building structure similar to buildings, your section is 15.4.1 as opposed to 15.4.2, which is for non-building structures not similar to buildings. So 15.4.1 will give you what you need, or most of what you need. As I said, it is more or less treated as buildings. Use table for the R value. You use table 12.2-1, but also table 15.4-1. And there is a reason for that. And we will discuss that. Calculate period by section 15.4.4. Here, there is a difference between buildings and non-building structures in the period computation. Okay. Now, why did we say for R values use table 12.2-1, but also table 15.4-1? In this table, that applies to non-building structures similar to buildings. We have done something That is not done anywhere else in AC7. There is a trade-off allowed between height limit and R value. Okay, let me try to explain. So the system here is ordinary steel concentrically braced frame. Ordinary concentrically braced frame of steel. Ordinary as opposed to special. Okay. The usual R value is 3¼ omega sub 0 is 2, C sub D is 3¼ no height limit up to design category C, but then 35 feet only, design categories D and E, and not permitted in design category F. Okay. Now you can definitely use that line, but then you have to deal with a 35-foot height limit in design category D. That may not serve your purpose. So we are being offered two alternatives. You can take the penalty of using R of 2½ rather than 3¼ That will increase your design force. So your new set of parameters should be R of 2½ omega sub 0 of 2 and C sub D of 2½ Design category up to C, there is still no limit, but look at this design category D, you now get to go up to 160 feet of height. 160 feet, E and F don't interest you, so I wouldn't go there. So from 35, you get the height limit extended to 160 feet for the price of reducing the R factor from 3¼ to 2½. If you are prepared to go all the way down to 1½ for your R, look at this, no height limit in design category D. Okay, so as I said, and I truly want to emphasize this, I don't know, for decades now, a lot of people have been asking for relief from special detailing requirements if we have a lot of strength sitting there for us. There are many buildings that are strong for reasons that have nothing to do with structural requirements. Okay, they are strong, maybe because they're supposed to be monuments. Okay. Anyway, in those structures, design category D, do we need to do special detailing? What is this detailing going to do for us? If the structure is really stiff and strong, it is not going to move in an earthquake. So what would all this detailing do? Anyway, that is the argument. There are number of, anyways, this is something that has never been allowed by ASC 7 until now. Things may always change in the future, but so far we have not relented on the requirement that in design category D, you shall as a minimum do special detailing. Design category C, you shall as a minimum do intermediate detailing. Okay? Now here, it is not exactly the same thing. Some of these non-ductile systems are allowed anyway, like this ordinary concentrically braced frame of steel is not a ductile system. We're still allowing it in design category D, but put a height limit on it. Now what we are allowing, and this is the only place, only for non-building structures similar to buildings, is a trade-off between R value and the permitted height limit. Okay, interesting concept. I hope the explanation has been clear. So with this system, you have a choice of an R of 3.25, which will give you 35-foot height limit in design category D, or an R of 2.5, which will take your height limit in design category D to 160 feet, or if you are prepared to go down to 1.5 for your R value, then you get unlimited height. Okay. Similar trade-offs are allowed for intermediate steel moment frames, intermediate reinforced concrete moment frames, ordinary moment frames of steel, ordinary reinforced concrete moment frames. Okay, so those are the 5 systems: the concentrically braced frame, and these for which the trade-off is allowed. But with, for instance, the intermediate reinforced concrete moment frame, to get to unlimited height, your R value has to be 0.8, below 1. Okay, so please take a look at this table 15.4-1. Very interesting table. Interesting things are happening in there. Okay, not similar to buildings. So you still have to look at 15.4.1, where it directs you. The R omega sub 0 and C sub D now comes from table 15.4-2. And the design base shear equations are the same, but the minimums are not the same, as I'll show you. And the period calculation is cannot be this. It is not the same as for buildings. Basically, you cannot use the approximate period that we use in building design. Okay, that is not allowed by chapter 15. Okay, so these are the design base shear equations that you are all familiar with by now. This is the descending branch, period dependent. This is the upper bound. This is the constant displacement part of the spectrum starting at T sub L. Now, the lower bound, remember 0.044 S sub ds I times W, but never any lower than 0.01. Here it is 0.03. Okay, this is a much higher minimum. Non-building structures not similar to buildings, much higher minimum. And the near fault minimum, I don't remember exactly what it was, is also different here for non-building structures not similar to buildings. This minimum applies only where the mapped long period quantity is larger than or equal to 60% of G, which is the rough equivalent of old UBC seismic zone 4. For non-building structures, we use I, not I sub P. I is the importance factor. It is given in section 15.4.1.1, which references table 11.5-1, where the seismic importance factors are given for structures. I is either 1, 1.25, or 1.5 as for building structures. Okay, no difference. This is not I sub P. Period computation. How do you determine T? The approximate period formulas do not apply. That's pretty much what this is saying. So this is the requirement for period determination for non-building structures. The fundamental period of the non-building structure, fundamental period, shall be determined using the structural properties and deformation characteristics of the resisting elements in a properly substantiated analysis. The eigenvalue analysis that we talked about involves stiffness assumptions as indicated in section such and such. Alternatively, you can use the Rayleigh-Ritz formula. Okay, many of us are kind of familiar with this, and I don't remember. I don't think I showed you an example. Anyway, this is reasonably easy to use. The W sub I, delta sub I, F sub I are explained here. The values of F sub I represent any lateral force distribution in accordance with the principles of structural mechanics. We typically take the design base shear distributed according to the code prescription, but you don't have to. As it says, it can be any lateral force distribution in accordance with the principles of structural mechanics. You shouldn't have a high force at the base and a low force at the top. That is not in keeping with the principles of mechanics. Anyway, the F sub I are the forces, delta sub I are the displacements obtained for those forces from elastic analysis, and what else was involved? F sub I, W sub I. W sub I are the seismic weights at the various flow levels. Okay, so this equation, I think you are, well, the main thing is the approximate period formulas are not allowed. It has to be rational period determination, which you can do on the computer using eigenvalue analysis, as we call it, or if you want to do simple hand calculation, it is the Rayleigh-Ritz formula that you can use. When I say hand calculation, the delta sub I has to come out of analysis. Okay, but then you can find the period by basically manual calculation. Okay, the particular non-building structures for which AC 7 chapter 15 gives you provisions are pipe racks. These are all important, very important things. Steel storage racks, electrical power generating facilities, towers supporting tanks and vessels, piers and wharves that are accessible to the public. If those are private piers, then not covered by ACE 7. This list is all similar to buildings. Pipe racks, steel storage racks, electrical power generating facilities, not all of them are necessarily similar to buildings, but those that are similar to buildings are covered. Towers supporting tanks and vessels, piers and wharves. Specific items covered in SC 705 that are not similar to buildings. Earth retaining structures, stacks and chimneys, amusement structures, special hydraulic structures, secondary containment structures, tanks and vessels. That's the section I was telling you has grown to the point that I can't even believe. Okay, there is a section on drip limitation for non-building structures. The drip limitations of section 12.12.1 for buildings need not apply to non-building structures, need not apply if a rational analysis indicates they can be exceeded without adversely affecting structural stability or attached or so without adversely affecting structural stability or attached or interconnected components and elements such as walkways and piping. Okay? Without adversely affecting attached or interconnected components and elements such as walkways and piping. If you can show that large deflections will not have adverse impact on walkways and things, then the drip limit for buildings does not apply. P delta effects shall be considered where critical to the function or stability of the structure. Okay. The final segment, this is not final. I have a little example at the back, which I probably should have put after the non-structural component, but anyway, it doesn't matter. Let us look at this. What is it? Non-structural component or non-building structure? Quite often, it's not that clear-cut. And Susan Doughty, who worked with me for quite a while, she wrote a paper some years ago with Bob Bachman, who is one of the authorities on in this field. Much of what you see in AC 705 for non-structural components in particular are because of Bob. Anyway, the two of them together wrote a paper, and the slides are basically out of that paper to provide an idea to engineers on this important topic. Non-structural component or non-building structure. Okay. So non-structural components covered by chapter 13 are the specific items are listed here, and there are a lot. So non-structural components on the left-hand side, non-building structures not similar to buildings are in the right-hand side circle, and there is no question that these things, amusement structures, hoppers, monuments, silos, storage racks, these are non-building structures. Okay. The question is about this intersection, chimneys, conveyors. They can be non-structural components or non-building structures. So these can be either non-structural components or non-building structures. Billboards and signs, bins, chimneys, conveyors, stacks, tanks, towers, vessels, cooling towers. So what are some of the differences between non-building structures and non-structural components? And Susan thought that a warning should be issued to the viewers. What you are about to see is for guidance only. Generalizations have been made. Generalizations do not always apply. And in applying these guidance, or any guidelines, actually, common sense is necessary. Okay, so these are definitely not hard and fast rules. These are just suggestions to set you on the right path. So what are some of the differences based on size? Non-structural components are small enough to fit in building, somewhere around 10 feet tall. The 10 feet is totally arbitrary. usually transported in one piece on a truck. Non-building structures are typically large. Not always, but typically. Designer always has the option of calculating both ways. You can take the same thing as a non-structural component designed by chapter 13. You can redesign the same thing as a non-building structure by chapter 15 and take the more conservative answer. That is always a choice. I do not know that too many people exercise this choice. Okay, going on with differences based on assembly location. Non-structural components usually requires a non-structural component usually requires no assembly at job site. Weight is likely small relative to structure's weight. A non-building structure, on the other hand, is usually assembled at the job site, largely because of their size. Differences based on construction or basis for construction. The usual function of a non-structural component is for architectural, mechanical, or electrical purposes, as we know. Non-building structures usually, usually constructed to resist gravity and lateral loads and also to maintain structural integrity. Okay, I don't know how useful that was, but anyhow, a lot of people have told us good things about that paper, so I thought that it might be of interest. Okay, a small example of the seismic design of this parapet. Okay, 900 millimeters, 9/10 of a meter tall. That's what sticks above the roof. These are the roof joists, the roof anchors. Anchors are 1200 millimeters center to center. I don't think we will get into those details. I don't know what has happened to concrete. This is a concrete wall, 180 millimeters thick. Yeah, that's what, 8 inches. 6 is 157.5 inches. Okay. Okay, so this is we are trying to design this parapet. Weight of the parapet per linear foot is 24.52.9 1.18. I don't know that everything is presented in the problem statement. Let me see. No, I did not give you the other details. Okay, so accept that to be the weight, 3.97 kilonewtons per meter of this parapet. The seismic lateral force, which would act at the centroid of the parapet, is given by AC equation such and such as F sub P equal to, I corrected these things last night and it still looks, so it is A sub P, S sub ds, I sub P divided by R sub P, 1 plus 2z over h w sub P. You have looked at that equation a number of times. We will use that equation now. Our I sub P is equal to 1. It's a parapet. It doesn't serve any essential purpose. S sub ds is 50% of G. That is kind of part of the problem statement. W sub P, weight of the parapet, this is calculated value, although I didn't give you the details that are needed for the calculation. 3.97 kilonewton per meter. A sub P, the component amplification factor, which is given in table 13.5-1 for architectural components. I told you it is either 1 or 2.5. If you go to that table, you will see that for parapets, it's 2.5. The H height of roof above the base is 6 meters. That was given in the problem statement. This 6,000 millimeters here. Okay, so that is H, and Z. Z, remember, is height to the location where the component is attached. The parapet is attached to the structure at the roof level. So our Z is also equal to H, is also equal to 6 meters. This is like a roof mounted equipment. Parapet is mounted on the roof or attached to the roof. R sub P, component response modification factor. If you go to the table 13.5-1, where we found A sub P of 2.5, the R sub P is also 2.5. So now we have everything that goes into this equation. 0.4 S sub ds is 0.5. What was before point? 0.4 A sub p, 0.4 A sub p, S sub ds, I sub p. So 0.4 A sub p is 2.5, S sub ds is 0.5. I sub p is 1 divided by R sub p of 2.5, and then 1 plus 2 times z over h. Z is 6 meters, h is 6 meters, times w sub p. All of that gives us 60% of the weight. The weight we said is 3.97 kilonewton per meters. So 60% of that would be 2.38 kilonewton per meter. There is a minimum on the F sub P below which you cannot go, and minimum and maximum, remember, so those simply do not govern. So the governing F sub P is 2.38 kilonewton per meter. This acts at the center of mass of the parapet, and the parapet is 900 millimeters tall. So the center of mass is half of that above the roof. So that is 0.45 meter times the 2.38 kilonewton per meter gives us 1.07 kilonewton meter of moment per meter length of the parapet. Okay, so for 1 meter strip of the parapet, the bending moment at the roof level is 1.07 kilonewton meter. So it's a very simple example. At the same time, I think it shows you application of the F sub P formula, which has multiple components in it. Okay, thanks very much. That's what I planned for today. This is our last seismic offering, and Bodhi is right. We are early. So anyway, I'm open to questions, and I would like to, before I open up to questions, I really would like to thank all of you for listening to long lectures. This is the 19th time that I have appeared before you. To listen to the same voice day after day cannot be all that enjoyable. And you have kept on coming, which I truly appreciate. And hopefully this will lead to better things. Okay, thank you so very much, and I'm open to questions.
Thank you, Dr. Ghosh. Yeah, we don't have a lot of questions till now. So I'll start from the very beginning. Dr. Ghosh, some of the questions are related to earlier sessions. So I
Hmm.
just want to tell you.
Hmm.
And this is something that I think you already replied once, but I will still read the question. So in BNBC 2020 table 6.2.19 for seismic design category D, the height limit for intermediate moment resisting frame system is 35 meters. But for dual system intermediate moment frame, it is 11 meters. So can you explain why the lower height limit for dual system?
So intermediate moment frame, the height limit is 35 meters.
Yeah, I think he's talking about the steel moment frames, not concrete.
Let me look up the table.
Yeah, because concrete moment frames is not even allowed in
Let
STCD.
let me look up the table. What is the number? This is the R values table, right?
Yeah, 6.2.19.
Maybe it will be easier for me to go to AC7. Okay, give me a second. Okay, so first he has an intermediate moment frame. Intermediate moment frame has a height limit of 35 feet in
Yeah, that
design.
is in AC7.
Yeah,
Yeah.
that's what he's saying, and it is true.
He's saying in BNBC it is 35 meters.
No, no, it cannot be 35 meters. It's 35 feet. I'm sure it's not 35 meters. Oh, I,
Yeah,
I see what has happened. So the 35 was not converted.
probably. Yeah.
35 feet is 11 meters. So intermediate moment frame of steel is 35 feet and
Yeah, in BNBC it is 35 meters. So that is wrong, I
wrong,
guess.
wrong.
Yeah.
It's 35 feet. And dual system with intermediate moment frame. Uh, Now, what is the shear wall?
He's talking about steel concentrically
Oh,
braced frame.
okay,
So
steel concentrically braced frame. Let me see.
that also has 35 feet.
Yeah, that is also 35 feet. So 35 feet in the second case was converted to 11 meters, and in the first case was not converted. So good catch. Yeah, it's just a mistake. It's 35 feet in a C7, no question. But the 35 meters is absurd for intermediate moment frames in design category D. I can tell you that it's not right.
Right. So in a building with basement floor, should the retaining wall, while analysis of the building, should the retaining wall stiffness modifier be same as shear wall or different?
No, the retaining wall does not enter into the analysis. You analyze the structure above the base, and the basement walls are typically below the base. So I do not know that this question arises.
I think the basement is not is analyzed for elastic, not inelastic deformability, right?
The
In
the
case
the
of
basement walls, if they're designed, it will be for the uh, the out of plane soil load. The soil loads it from the outside, and as far as the entire basement goes, earthquake increases the soil pressure on one side and decreases it on the other side. And that needs to be taken into account in earthquake situations. But none of this enters into the analysis of the building.
This will answer the other question also. So it's moving on. What is the return period for a design-based earthquake level and a service level earthquake?
There is no such thing as a service level earthquake. At least I am not aware of any. Sometimes, well, first of all, the first question is what's the return period on the design basis earthquake or something like that, on the design earthquake, right?
Yes.
Hmm?
Yes, you're right.
Okay, so the answer is that it is uh, not a fixed number. The design earthquake is 2/3 of the maximum considered earthquake, which has a 2,500-year return period. Okay, so when you take 2/3 of 2,500-year earthquake, that has a variable return period. In the United States, where I know the numbers, that number varies from 500 years in coastal California all the way up to 1,000 years or more on the East Coast. Okay, something in that range. I believe there are places where it can be as high as 1,500, but that's probably uncommon. So anyway, it's a variable return period, uh, and that would be true of Bangladesh as well. So it will be something I suspect in the 1,000-year range, but it is not a fixed number that I can give you. Now, there is no such thing as a service earthquake, as I said, but sometimes a building is required to be completely functional, serviceable, and so forth under what are called frequent earthquakes. And those earthquakes uh, can have a return period. It depends on the design criteria. The the return period that typically I have seen varies from 25, 35, 40 years, something in that range. So very short return period. The idea is that nothing will happen to the structure in those frequent earthquakes. But it's not in BNBC, it's not in ASC 7. We do not talk about service level earthquake. That doesn't exist.
So this is a question, long question actually. So why have you stated that this is a vague provision in BNBC when this is also a recommendation from NERP? Um,
What did I say? What kind of a provision?
vague provision. Like, yeah. So he's saying that a similar provision is exists in NERP. So why did you say that it is a vague provision in BNBC?
Oh, vague.
Yeah, vague. Yeah, that only.
When I said today, that language is in our provisions,
Yeah, that's
that
what he.
doesn't make it any less than vague. So maybe there is commentary in out that explains it. I don't know. Yeah, anyway, what's the rest of the question?
Yeah, then he just describes the provision basically. So where the individual weight of supported components and non-building structures with periods greater than 0.06 seconds exceeds 25% of the
Yeah,
total size.
anyway, if he understands it, I would like to read this. Yeah, okay. Yeah, that's fine. So it's good to know that that is taken from the NAR provisions. I'll check it out.
Which method is used to determine displacements of non-structural components?
You do elastic analysis just like for any structure. What other method? I don't understand.
If a generator is placed on a floor,
Hmm.
then what are the design philosophy for this floor and the supporting element?
What does it mean, design philosophy for the floor?
The criteria, I think, how to design that floor. Probably that's what.
You design the floor as a diaphragm by the diaphragm design force that I talked about. Was it yesterday? Yesterday, I think. Okay, so you do not design the floor for the F sub P force that we calculate in chapter 13. That is for equipment mounted on the floor. There is a bit of illogic here, but that's what AC 7 requires. The floor has to be designed for the diaphragm design force at that particular level, the F sub px. Okay? The equipment and the attachment have to be designed for the F sub p force. And that's where this requirement comes in, that you have to apply it in two orthogonal directions and things like that. So I don't know that I can tell you anything beyond that. Read the question again.
Okay. If a generator
Yeah,
is placed on a floor,
yeah.
then what are the design philosophy for this floor and the supporting element? I don't know. Is it talking about floor vibration? I don't know.
I have no idea. I don't know. Uh, yeah. Anyway, I would repeat the equipment and the support shall be designed for F sub P. The floor shall be designed for F sub Px. If there is vibration concern, that is not covered by the code. ACI 31819 has good commentary. There is literature available, but there is no codified method for taking care of vibrations. And okay, that's about as far as I can go.
For a multi-storied building constructed for cattle, is this a non-building
Concentrate for what?
cattle?
Cattle. I see.
Yeah.
Hmm.
Is this a non-building structure?
That is a good question. I think the answer is yes. Generally speaking, if people do not live or habitually work in a particular building, that building is a non-building structure. So if it houses cattle, people don't sleep there with the cattle. They just go in and out. Yeah, it would be justified to design it as a non-building structure. That's a good question. Yeah.
And the same about a public toilet or passenger shade.
Uh, yeah, yeah, those are again the key is that people don't live there or work there. They go in and come out. Yeah, so
So these few of the questions have been answered in last lectures. I don't want to repeat it. Basically, it's
mm,
very straightforward.
mm.
So what should be the allowable limit for top lateral deflection of single-story steel gable frames against wind loads?
Say that again.
What should be the allowable limit for top lateral deflection of single-story steel gable frames against wind loads?
You have that just one limit in BNBC. I don't. I may not find it that easily. It was covered in one of the earlier lectures. Okay, it is section. Okay, what BNBC has to say is to be found in section 1.5.6. That applies to all structures, including the one he's describing. BNBC section 1.5.6.
Okay. Will this program continue for another batch? I think he's talking about the Essence training.
I hope not. No, this is it.
We consider the. It's a big question again. So I will read it slowly, Dr. Ghosh.
Mhm.
If we consider the floor height of a building as 3 meters and approximately a 20-story regular building can be designed through static analysis in seismic zones 2, 3, and 4 as per section 2.5.6. But as per section 2.5.8, dynamic analysis is essential for regular buildings with height greater than 40 meters, 13-story approximately, in zone 2, 3, and 4. Which one will be considerable?
Yeah, this is rather difficult to. I need to look. Should I take the time? So first section is 2.5.6.
Yeah.
Other people will get bored.
Meanwhile, let me see what I can answer.
So read what he says about 2.5.6.
Just a second. So he's saying that for a regular building with floor heights 3 meters and approximately 20 stories,
So he has
uh,
total height of 60 meters.
yeah,
Mhm.
it can be designed through static analysis in seismic zones 2, 3, and 4 as per section 2.5.6.
Let me find that static analysis procedure. Oh, yeah, I see what he's. Yes. So this requires that the building period be less than 2 seconds or 4 times the transition period. So he probably satisfies that. So according to this section, he can do static analysis. Okay, then what is the other section? Body.
2.5.6. 5.8.
2.5.8. Yeah, I noticed something like this. There is a gap. So 2.5.8 is dynamic analysis methods, buildings with height greater than 40 meters in zones
Yeah.
3 and 4. Yes, okay. Yeah. Yeah, I noticed when I read that there is a gap, and which one will govern is the general rule is the more specific provision governs. In this case, both are pretty specific, although I would say the second one, 258, is probably more specific. Regular buildings with height greater than 40 meters, zone 2, 3, 4. Nothing can be more specific than that. So, yeah, no, this is an excellent question. There is a problem created by the BNBC provision. If you ask my opinion, it is the more specific of the provisions, which should be 258, that would govern.
Okay. So that is answered. So it was a very good question.
Yeah, excellent question.
For drift calculation,
Mhm.
the deflection difference should be taken. Should we take it in the same vertical plan, or we should consider the maximum deflection of below floor level and maximum deflection of upper floor level at any point of a floor?
No, those are always two vertically aligned points. You take a point on the upper floor and a vertically aligned point in the floor below. It's not the maximum deflection anywhere in the top floor and whatever. No, vertically aligned points always.
Please explain overturning moment when we analyze only for dead load moment, self load, or including partition wall. We know that the factor of safety should be greater than 1. Any specific value of this factor of safety?
I don't understand the question.
When we analyze only for dead load moment.
No, where did it start? Please explain.
Explain regarding overturning moment for dead load moments only. That's what he's saying.
There
And what is
is
the factor of safety associated with it?
if a structure is not laterally displaced, then there is no dead load
No.
moment.
Yeah. Yeah.
So I do not know. Typically what we do is, so lateral load is trying to destabilize the building. So we calculate the moment due to lateral load, and then the moment due to dead load tries to stabilize it. That's the moment in the other direction. So the moment due to dead load has to be larger than the overturning moment due to the lateral loads. And the factor of safety, I do not know. It varies all over the place. 1.5 is a good number that many people have used through ages. So if that is the question, that is a basic stability check that many of us do. And 1.5 is not a bad number.
Okay. Uh, So, when a building is having extreme torsional irregularity, to satisfy redundancy condition, we have to remove the um, members of. Okay, let me rephrase this question. For redundancy condition 1, due to torsional irregularity greater than 1.4, it is not applicable for the structure and should go for member removal. But member removal of extremely torsional irregular building is also extremely irregular.
Yeah, so in later editions, we have specifically said if you have extreme torsional irregularity, it is non-redundant. The row factor is 1.3. I don't remember whether we did it in AC 710 or 16, but now it is very specific. What he says is true. If it is extremely torsionally irregular to start with, then there is no point in going through member removal and so forth. It will be extremely torsionally irregular at the end of it. So now we say that those are redundant. Those are non-redundant buildings with row of 1.3.
Okay, this question you have answered before. Um, can we get a list of non-building structure according to ACI, AC, or any? I think that list that you provided is good, right? Like,
It is, look at SC 7 chapter 15 and you will have your list because these R omega sub 0 are given.
okay. So next question is, if we design a toilet block in a school, do we need to consider earthquake and wind load?
You need to consider earthquake and wind load for everything. I don't even understand the question because it's a toilet block, you may not. So, when somebody is sitting on a toilet, you don't want him to fly away if a windstorm hits. I don't know. I don't understand why the question arises.
Mobile tower on a rooftop and building. Which analysis should be performed for complete assessment? It is very common in Bangladesh.
Say that again.
A mobile tower on a rooftop or a building.
Mobile
What's
tower.
yeah. Yeah.
Okay, and what's the question?
What analysis procedures should we adopt for complete assessment?
I have no idea. Without looking at the specifics, I'm not familiar with this. They may be common in Bangladesh, but I'm not familiar. So, have to look what it means. Mobile means what? There are rails, or, I don't know. We have to have more specifics before.
Mm. ACI 31814
Hmm.
for
Hmm.
main tie hooks is not 135 degrees, it is 90 degrees. In figure R25.7.2.3a. Please explain.
What do I need to explain? I don't know.
So why is it not 135 degree and it is 90 degree?
What? How did he decide that it has to be 135? I don't. Let me. What's the figure number?
R25.7.2.3a.
R25. R25 7. Tell me one more time.
25.7.2.3a.
H or A?
A.
A.
Yeah,
Okay, so 25.7.2.3A.
right.
Okay, what's the question now?
He's saying that why the main tie hooks are not 135 degree and it is 90 degree.
135 is needed in seismic applications. This is chapter 25. This is not seismic. So that is the short answer. If you have to use that in design category D, actually even in C, then you would need seismic hooks, and then they will be 135. Chapter 25 is a non-seismic chapter, you have to understand. 18 is where seismic detailing is to be found. And I went over all of that in earlier lectures. So the answer to your question is this is essentially what you see in that picture can be used only in design categories A and B. Okay. And
Uh,
you do not have A in all of Bangladesh. B, I do not know. You don't have in the Dhaka area. So you cannot use 90-degree hooks as shown in that picture. Your picture should be from chapter 18.
okay. So I think we still have time. Yeah, other questions are also you have gone in length over them in your previous lectures.
Mhm.
So in section 2.5.5.4 for re-entrant corner structure, there is a term A, that is capital A. Can you please explain what does it mean? Is it the gap or is it the length of structure?
2554.
Yes,
What happened today? I wasn't getting this kind of questions before.
I am also checking.
So, okay, tell me the question again in 2554.
For re-entrant corner structure, there is a term A,
Mm.
capital A.
Mm.
So he wants to understand what is that.
That's the projection as shown in the picture. If A sub 1 is more than 15% of L sub 1, you have a non-entrant corner irregularity. If A sub 2 is larger than 15% of L sub 2, then you have an irregularity. So the A is the length of the projection as clearly shown in the picture. I don't know what was the question?
So he was thinking, is it the gap or is it the length of the structure that it can prolong? Project basically, that's what he was saying. So prolong, I think by prolong he means project.
Huh?
I think by prolong he means project.
I honestly don't understand the question. The picture shows a plan view, okay?
Yeah.
And A sub 1 is the length that is clearly shown.
Let me also go to the section.
There is no gap here. There- there- I don't know how to describe them. They're typically called projections. The picture is very, very clear. I do not know what the confusion is.
Yeah. Okay, this is 2.5.5.4. Yeah, he's talking about it capital A1 and capital A2. Yeah, you're right.
Yeah. So capital A1 and capital A2 are very clearly shown in the picture. Those are the lengths indicated. And if A sub 1 is larger than 15% of L sub 1, or L sub 2, A sub 2 is larger than 15% of A sub 2, then we have a reentrant corner irregularity. That's what it means.
So this is just a general question, I guess. So for a super tall building like Burj Khalifa,
Hmm.
it needs to satisfy the wind sway limitation.
Mm-hmm.
Say it has to satisfy according to BNBC. The allowable sway is he calculated 828 divided by 500, 1.656 meter. This is huge. So
Hmm.
how can you make the building livable? Because so
Yeah, buildings of that height are not done by prescriptive provisions of the code. So I do not know uh, exactly how. First of all, there was very sophisticated wind tunnel testing on the building, and they must have satisfied the government of Dubai that the that the deflections were tolerable, and they must have had to go further and go into occupant comfort, which so deflection, if you take first derivative of deflection, it is velocity, second derivative is acceleration, third derivative, I don't remember what it's called, fourth derivative is related to human comfort. And that has to be kept within limits. So a building that high, you will not just try to apply BNBC and say height over 500 is my limit and I'm done. There is much more to it than that. Even the floor accelerations may be an issue for things that are mounted on the floors. So I do not know. Without talking to the engineer, I know the engineer, I can maybe find out, but no, I do not know offhand how it was done. But it definitely did not go by the height over 500 criterion. No, no, that I'm sure of.
okay. Should we connect pile cap or footing foundation with beam for seismic as per section 2.5.2.2?
Yes, tie beams are required in seismic applications.
Okay, so that was a simple answer.
Mm. Yeah, this is an SAI 318.
If a floor beam is supported to another beam, then if the beam width is narrower, then how to ensure the development length of the longitudinal rebar of the supported beams?
Yeah, there was a similar question, a narrow beam coming into a shear wall, and I do not know without. This have to be solved on a case by case basis, and I do not know. You can, if somebody sends a sketch, one can try. Yeah, I do not know how to answer in a general fashion these detailing questions. Yeah, that's kind of a negative note to end on, but that's the honest answer. I mean, given the specifics, I could come up with something, but there is no general rule. Except you have to do what you have to do. You have to develop the bars. You have to anchor them properly.
Yeah.
If everything fails, you have to go to mechanical means. Okay, maybe one more and that's it.
Yeah, I'm just looking at the question. Just looking at which question should I read. Do every uh, does every floor slab uh, okay, should every floor slab be designed as diaphragm for a moment resting frame system without shear walls?
Whether you design floors as diaphragm has nothing to do with whether you have frames or shear walls. The a slab will act as a diaphragm whether you design design it to act as a diaphragm or not. It's just natural. The slab is there. If wind blows on your building, the slab will go into in-plane bending. That is diaphragm action. The question is, do you need to do anything about this? Because your slab already has a lot of reinforcement that you put in there for gravity. And much of the time, particularly under wind, that reinforcement is good enough for diaphragm action as well. But then if it is high seismic, you may want to check whether the reinforcement you already have is sufficient. Maybe all you need to do is to rearrange the reinforcement a little bit. So what I'm saying is that your slab will act as diaphragm irrespective of your lateral force resisting system, whether those are frames or shear walls. A frame building will move more, so that is something it is good to be aware of. Anyway, under lateral loads, the slabs will bend in their own plane. There will be diaphragm action. The diaphragm action may not require you to do anything extra. What you have done for gravity may be good enough, and quite often it is. Under wind, most of the time we do not check diaphragm action, good or bad, right or wrong, we typically don't check. If it is seismic, particularly high seismic, then it is a good idea to check. And it's not only a good idea, it's a requirement of ACI 318 that you specifically provide for diaphragm action. And that again does not depend on whether the seismic force resisting system is frame or shear wall.
Okay, Dr. Hus, I guess this uh, answers most of the question. I think this is the last session, so they were
Yeah.
asking all the questions that they had.
Okay.
So yeah,
Oh,
thank you, Dr. Ghosh, for this wonderful series of webinars.
thank you.
And
Thank you so much. it's it's hard to believe that it came to an end. So okay.